In the previous lesson, we learned how to write state space models for physical systems. Now we go in the other direction. Given a state space model, how do we find the transfer function? We will derive a general formula, verify it with the DC motor example, and then show the state space equivalence of standard transfer function blocks. Starting from the state equation, x dot equals ax plus bu. We take the Laplace transform of both sides, assuming zero initial conditions. The left side becomes s times x of s. The right side becomes a times x of s plus b times u of s. Rearranging, s x of s minus a x of s equals b u of s. Factoring out x of s, we get si minus a times x of s equals bu of s. Here, I is the identity matrix. Solving for x of s equals the inverse of si minus a times b times u of s. Now substitute into the output equation. Y of s equals c transpose x of s plus d u of s. This gives us y of s equals c transpose times the inverse of si minus a times b plus d all multiplied by u of s. Therefore, the transfer function is g of s equals c transpose times the inverse of si minus a times b plus d. This is the fundamental relationship between state space and transfer functions. Let us verify this formula with the DC motor. Recall from lesson 15. A has minus Ra over La and minus C phi f over La in the first row, C phi f over j and 0 in the second row. B is 1 over La and 0. C transpose is 0 and 1. D is 0. Computing Si minus A, we get S plus Ra over La and C phi f over La in the first row, minus C phi f over j and s in the second row. After computing the inverse and multiplying through, we obtain g of s equals C phi f over La j divided by s squared plus Ra over La times s plus C phi f squared over La j. This matches exactly what we derived in lesson 14 using block diagram simplification. Now let us find the state space models for standard transfer function blocks. First, the integrator with g of s equals 1 over s. The state equation is x dot equals u and the output is y equals x. So a equals 0, b equals 1, c transpose equals 1 and d equals 0. Applying the formula, g of s equals 1 times the inverse of s times 1, which gives 1 over s. Confirmed. Next, the first order lag with g of s equals k over 1 plus st. The state equation is x dot equals minus 1 over t times x plus k over t times u. The output is y equals x. So a equals minus 1 over t, b equals k over t, C transpose equals 1 and D equals 0. Applying the formula, Si minus A is S plus 1 over T. Its inverse is 1 over the quantity S plus 1 over T. Multiplying by K over T, we get G of S equals K over T S plus 1, exactly as expected. Finally, the second order lag with G of S equals K over 1 plus 2dts plus t squared s squared. This needs two state variables. We set x1 dot equals x2 and x2 dot equals minus 1 over t squared times x1 minus 2d over t times x2 plus k over t squared times u. The output is y equals x1. The A matrix has 0 and 1 in the first row, minus 1 over t squared and minus 2d over t in the second row. This pattern generalizes. Any nth order transfer function needs n state variables. Here is a practical rule. To read state space equations from a block diagram, identify each integrator. The output of each integrator becomes a state variable. Then trace the signals to write each state derivative. For example, in a feedback loop with gain k and an integrator, the integrator output is the single state x. The state equation becomes x dot equals k times the reference minus x. This systematic method works for any block diagram, no matter how complex. To summarize, we derive the transfer function from state space as g of s equals c transpose times the inverse of si minus a times b plus d. We verified it with the DC motor, confirming it matches the result from block diagram simplification. We showed the state space equivalence of the integrator, first-order lag, and second-order lag, and we learned to read state equations directly from block diagrams by identifying integrator outputs. In the next lesson, we will study nonlinear system modeling.